Okay, let's take a look at the electric force. The electric force is given by KQ1 times Q2 over R squared. K is a constant, right? So the force is proportional to what? Well, it's proportional to the two charges, and it's proportional to the distance squared, and that's an inverse relationship. They lots of times would refer this to as an inverse square law. Those of you remembering gravity, gravity is very similar. Right, when we looked at the force of gravity, a lot of comparisons here. It was big G, M1, M2 over R squared, and so this was also another inverse square law, and gravity was the attractive force between two masses, and G was a universal gravitational constant. I guess maybe the only difference between the gravitational force and the electric force is that this doesn't have to be just attraction, right? This can be repulsive, or this can be attraction. So we talk about opposites attract. So if we have a positive charge and a negative charge, those two charges are going to attract each other. And if we call this Q1 and this Q2, so let's say that Q1 is positive and Q2 would be negative, there would be an attractive force. And I just want to be clear that it doesn't matter which one's bigger or which one's smaller, which one's positive and which one's negative. The force of attraction that Q1 experiences due to Q2 is equal to, no matter what, equal to the force of attraction that Q2 feels versus Q1. Again, Newton's third law would say that it doesn't matter. Both of them are necessary in order to have an attraction, and they both feel the same force. Now, I would say that if, let's say, Q1 is somehow much more massive than Q2, well then, of course, their acceleration rate wouldn't have to be the same, because if they both experience the same force, but one has a much bigger mass, then the other one is going to have, if one has a much bigger mass, then it will experience a smaller acceleration. I never said their accelerations were the same, but no matter which one's bigger, which one's smaller, which one's the positive charge, which one's the negative charge, the force of attraction between the two is the same, because it takes two charges to attract. So sometimes it'll be a big Q and a small q. It doesn't matter. Most of the time, we can just write it as Q1 and Q2. And K is Coulomb's constant. Coulomb's constant. And that is 9 times 10 to the 9th. Remember, you typically are dealing with very small charges and smaller distances. So K actually is in a big number, and F, of course, is in newtons, because it's a force. So they can ask all sorts of questions. You do have to remember that it is a vector, and so then it does get annoying when you start talking about, let's say we have a new situation. So here's our coordinate system, and let's put some charges. So let's say we have that guy there, and that guy there, and that guy there. And then we want to have this fourth charge right here. Okay, so this is some Q1, Q2, Q3, and let's say that this one is positive. Let's make that negative, and we'll make that positive, and we'll make this fourth charge, Q4, well, we'll go ahead and make it positive. Okay, and this is some positive charge. Okay, so remind yourself that each one of these will apply a force to Q4, and you have to decide based on their individual signs and their individual distances how big the force is and what direction the force is. So let's look at what would Q1 do to Q4. Well, Q1, since these are both positives, Q1 is going to repel Q4, and its force is going to be directed this way. So we have some force acting on Q4 that's to the right. Now, how big is that? Well, the magnitude of that force is just K, Q1, Q4 over R squared, where that R would be this distance. Okay? All right, what would Q2 do to Q4? Well, this is a negative sign, and so it's going to attract. So you're going to have that force on it. Again, the magnitude of that arrow is given by K, Q2, Q4 over this distance squared, right? R is the distance between the two charges. And then what is Q3 going to do? Well, this is a positive and this is a positive, so Q3 is going to repel. So you're going to get something that looks like that. Okay, so let me call this F1. We'll call this F2, and I know it's Q2 and Q4 both interacting to cause that, and we'll call this F3. Okay, those are the forces due to those other charges in combination to Q4. Okay, so then what is the total force? Well, you're going to have to break this down into vectors. You're going to have to do x hat, and you're going to have to do y hat, and we'll call this angle theta. And so in the x direction, you're going to have F1, which is all in the x direction, but then F2 is going to be to the left and down, so it's going to be a minus F2 cosine theta in the x direction. And then y direction, we're going to have F3 that's up, but we're going to have F2 sine theta, which is down. Those two are going to give you their components, and then from there, you can kind of, see where everything's at. And again, these magnitudes are going to be completely determine whether the final force is actually to the right, or it's up, or down, or it's up and down, or excuse me, up and to the right, or up and to the left. It kind of just depends, and these forces depend on these charges. Remember, what we said is that F1, in our diagram, F1 was the force due to Q1 and Q4. So if this distance was, let's say, D, and this distance was L, just random distances, then F1 will be K, Q1, Q4 over D squared. F2, the magnitude of it, F2 is going to be K, Q2, Q4 over this distance. Well, that distance squared, well, that's D squared plus L squared, and sometimes I just wouldn't even write the square root because I'm just looking for this distance squared, which is D squared plus L squared. And then F3 was due to these two charges, K, Q3, Q4 over that distance squared, which was L squared. So the magnitude of those charges, then again, the angle you could find out by doing inverse tangent, right? Theta is inverse tangent, in this case, of L over D. So once you know the angle and you know the magnitudes, if you knew the charges, then you could add up the vectors. And again, you just got to remember, forces are always vectors. And so it's kind of annoying sometimes. But draw the vectors, add them up just like you did old school vectors with forces again, because it's an electric force. We could teach this, 4 months ago, and we could have done it with forces when we did forces in September. That just happens to be an electric force, so it's due to the fact that we're dealing with two charged particles, and we can go through all that other stuff. Lots of things they do like to do is they do like to do stuff like this. They want you to use some of your electricity stuff to find the net force on something, and then use it to figure out, well, how fast this thing is moving. And just remember, if you know the force and you know the mass, you can figure out the acceleration. If you know the acceleration, assuming it's a constant force, again, that's not always the case, but if it was some constant force acting on some charged particle, then you could even use the v squared equation. You can do all this other stuff. And again, this is only true if there's a constant force, but let's say you came up with a scenario where there was a constant force, you can end up doing the v squared equation to figure out how fast it was moving after a certain distance and so on. Okay, so the electric force is given by this. It can attract or repel, and I gave you examples of both of those. It's an inverse square law because the attractive force falls off like 1 over r squared. So if I double the distance between my charges, so if I have charges like this, and they're a certain distance away, d, and if I double that distance, what did I do to the force? Well, if these two experience some electric force of F, what do these, and again, doubling R, this is only 1/4 of F. And again, you gotta understand that relationship, and they're gonna ask you questions like that. Okay? Maybe one other question. They might do something like this. They might ask the question, where can I put a third charge so that it doesn't experience a force? So let's say I have a charge here of, we'll give these a little numerical thing, how about a +4 here? And a +1 here. Okay? And I'm going to take a third charge. Where on this line, or maybe over here or over here, where can I put this third charge so that the third charge has no net force? So I want to put a Q3 on there, and so that the net force on it is 0. Okay, let's think of that scenario. And so if you think of the magnitude of the electric force, it's KQ, Q over R squared. And so if this charge is going to always apply a bigger force to my third charge than this one is, if they're the same distance, well, what happens if I make it closer to this one? And so when you think about it, if I put my third charge right about there, Q3, then this force, right, and this is a positive charge, this force is going to repel it, and this force is going to repel it. This is 4 times the charge, so then this one has to be, well, hopefully you're okay, the fact that this distance has to be d if this is some 2d. You see how those two forces balance? And hopefully we can go through this and you can think about why that's true. So think of what this charge does to Q. So we'll call that one, the red one, K times some 4 times some Q3 all over 2d squared, where this guy, so that's the red force, that's this force going that way, and then this guy has some blue force going that way, but the blue force would be K times 1 times Q3 over d squared. You see how those balance? Since this is 4 times the charge, but it's double the distance, doubling the distance squared makes a factor of 4, and so those cancel out. So if you put this third charge right there, I guarantee that these then will be balanced forces. And again, we're only looking at the net force on Q3, and it doesn't even matter whether Q3 is positive or negative. If it's positive, then this one will push it and this one will push it. If it was negative, this one would pull it and this one would pull it, and they'd still balance. Okay, and the red and the blue just would have both switched directions, but the magnitude of their forces are the same. Okay, so they like to ask questions like that. They also, what if it was a positive and a negative though? Okay, so what if it was a positive 4 and a negative 1 charge? Well, think about it for a second. If I put it anywhere in here, let's say I'm putting a positive Q3 in here, the +4 is going to push it, and the -1 is going to pull it. So anywhere in here, well, both of them go this way. So nothing's going to cancel, right? If I put any charge in there, any charge Q3, and assume Q3 is positive, this guy is going to push it. But if this is a positive, this negative is also going to attract it. And again, if this was a negative, this would attract it and that would push it, and they'd both be going left. So I can't put Q3 in there, but what I can do is put it over here. Okay, so that doesn't work. That position doesn't work to balance it, but I can put it over here somewhere on this line. Like here. About right there. Okay, if I put Q3 here, okay, let's say this is a positive, then what's this guy going to do? Well, that guy's going to push it, but that guy's going to attract it. And I'm just going to make sure those arrows are the same. And again, it's going to be the same thing. If I put this charge a distance d from here, and this is a distance d, do you see how this is a distance d from the Q, and this is a distance 2d from the Q? And 2d will end up canceling that factor of 4 created by the charge. And so whatever this distance is, if this is 1 meter, then put it 1 meter over here. And again, it's all about these ratios. Now, I agree, I am making it very convenient because I made this a square. You know, if this is 4 or 9 or 16, it's kind of very predictable where it's still very doable if this is a 3 or a 5 or a 2 or something. It just ends up being that you need to be the square root of 2 bigger. So it gets a little dicey in terms of how to figure that out, but the math still works out. You're still just setting these two things equal to each other and making them cancel, right? What if the negative was the bigger one? Okay, so what if it was positive 1 and then a -4. Well, then where would you want to put it? Well, then you can't put it over here. You can't put it closer to the bigger one. You got to put it closer to the smaller one. Oops. You know what? Let's make this. Let's not even make it a 4 this time. Let's make it a -9. -9. And then you're what? You're here. And I will show you. Doesn't matter whether that Q3 is some positive or some negative. If this is a distance d, this needs to be 2d. And why? Think about it. This force, let's say this is a positive, this guy's going to repel, and this blue would attract. And again, you want those equal to each other. So this red are these, k times 1 times Q3 over d squared. The red, meaning, or no, sorry, this was the red, and this is the attractive blue, k, and again, we want those magnitudes equal, times 9 times Q3 over what? Well, how do I know it was a 2D? Well, because I know I needed a 3D squared, because 3 squared and 9 cancel, and then these two magnitudes are equal. And again, I dropped the negative sign because I knew I wanted the magnitudes of them equal. I already knew that one was attracting or repelling and one was attracting. Okay, and again, if you just put an x there, you'd get x is equal to 3D, but I kind of just knew the answer. Okay, so they do love to ask questions like this with electric force, and you're finding where can you put some third charge, and hopefully I've proven to you that the sign of the third charge doesn't matter, so that the net force on it was equal to 0, and you can kind of balance it out. Okay, so this is the electric force.